Okay, as if the last question in that last note wasn't enough math, we're doing some more. And because this all has to do with triangles and triangles that you make yourself, this has to do with trig. So make sure you have your calculator on degrees for now. At some point, this may switch to radians. I can't remember if it switches in the middle of high school vectors or if you need to do that in beyond high school vectors. So anyhow, what we're doing now is we're talking about rectangular components of vectors, meaning if you're given a vector that has some, I'm going to say slant or slope to it, that is, I'm going to call it vector F, capital F for force. And this is vertical, which I'm going to do in red. And this is horizontal, so we're going to note them as vector F vertical and vector F horizontal. So we're going to use a whole bunch of communication tools that you can't let go, even if you're feeling a little lazy. Meaning that we're talking about vectors, make sure you keep the vector hats on. If you mean vertical, then you put down the little v as a subscript. If you mean horizontal, you put down the little h as a subscript, and if you mean neither one of them, then you take it off. Because if you don't have them there, it means something totally different. So you can't lose your communication. So I'm going to explain why these two formulas are the way they are, in case you don't want to memorize them. And that is because because it's rectangular, that means that you're talking about 90 degrees. You're talking about vertical, straight up and down, compared to horizontal, straight side to side. So you have a 90-degree angle in this triangle. And I've situated my triangle here in this way, rather than going off in the other direction or upside down, even though there's no upside down triangle. So here's my theta. Here's my angle that this vector F is making with the horizontal. And if you go back to the olden days of trig, if this is your angle, then this is opposite, this is hypotenuse, this is adjacent. So if I'm looking for, let's say this first of all, and I'm going to do this in red, then I'm going to need this measurement here and this measurement here, and that's O and H. So O and H is sine. So sine theta is equal to O over H. And we're not talking about vectors, we're talking about the length of the vectors. Then if you do a little cross multiply, you'll get 1 times the magnitude of the vertical vector equals, cross multiply in the other direction, the magnitude of the original vector times sine theta, and you get this formula. So it's not a formula that doesn't have any logic to it. It's a formula that has logic from grade 10. Now let's do it again with blue. So I'm just going to take a moment to get rid of these two things. And if I want to do the blue vector, it means that I need this information, and I need this, and that's A and H, and A and H is cosine. So cosine is A over H, not the vectors themselves, but the magnitudes of the vectors. Then I'm going to do a quick cross multiply just like before. 1 times the magnitude of the horizontal vector is the magnitude of the horizontal vector, cross in the other direction and get this, and that creates this formula for you. So the formulas do not come out of nowhere. They come out of trig. So knowing all there is to know about trig that you've been taught before today is kind of handy. All right, so let's do some work with this. And there are purposes, you just have to wait. So determine the horizontal and vertical vector components of a force with a magnitude of 43 newtons acting at 15 degrees counterclockwise from the vertical. So first thing is, I know we've dealt with it before, if you're following along with the videos, but this is a force measurement and it's newtons. Unimportant for this question, important for physics. Okay, so I'm going to actually use a ruler for this. So here is my vertical. And it says that I have a vector with a magnitude of 43 newtons acting at 15, so it's a vector, so I need my arrowhead, 15 degrees counterclockwise from vertical. So the hands of a clock go this way. So counterclockwise means that it's going in the opposite direction. And I'm just putting it arbitrarily, again, arbitrarily, compared to the vertical. So it doesn't matter if you put it, no, I'm going to leave it black. Doesn't matter if you put it there or if you put it here or here or here. I'm just going to leave it there because I have lots of space. One thing I do have to do is say that this is 43 degrees and say that this is 15 degrees. Oops, don't let me do that. (15 degrees and 43 newtons. So what I want to do is and I kind of did draw that there for a purpose. What you want to do is you want to associate that with a grid. So that's not what I meant to do. Let's see what happens. So there's a couple ways to do this. Personally, I would go back to the olden days of advanced functions and grade 11 functions, and I would remember that if you've got a grid, your angles, when you create them in each quadrant, should be closest to the x-axis, meaning they're in the bow tie. So what I really want to do is I want to make a vector in this direction. I didn't pick my vector symbol. A vector in this direction and a vector in this direction. So I'm kind of mimicking this picture. So I am going to turn this one into red, my vertical vector, and this one into blue, my horizontal vector. Now, I prefer, personally, not to use the formula and to use trig, because my trig is better than my formula memorizing. But before I do that, I need to find this corner, because that's in the bow tie. So that's 180, it's 90 minus 15. Which is 75 degrees. Now, of course, you can do this vector and this vector using 15 degrees, but I like to keep my math very standard so that I'm doing the same thing over and over again, regardless of the course. So, blue pen, I want to know the component, and this is the horizontal. And I want to know the component, and that's the vertical. All right, you can do whichever one you want to first. I'm going to use trig again. So opposite, adjacent, hypotenuse. Even though there are formulas, I'm letting it do the work. I'll do the red one first. So I've got opposite and hypotenuse. So sine of 75 degrees is equal to the magnitude of the vertical component over the magnitude of the force itself. That's sine, don't know why my hand's not working. Lucky this is my last note of the morning. Sine 75 degrees is equal to, what I'm looking for is that over 43. If you need to, feel free to put the 1 down, but 1 times that is itself equals 43 times sine 75 degrees. And you can leave it like that if you choose, or you can turn it into a decimal. And get 41.53. Newtons. And then we get to do it all again for the blue. So the blue is adjacent compared to the hypotenuse. So that's cos. So cos 75 degrees is equal to adjacent over hypotenuse. Put this over 1 if you need it. There's lots of symbols, and they're just as annoying for me as they are for you. Times 75 cos equals 11.13. Okay, so we have our vertical component and we have our horizontal component, and that's all that was asked for. But I do want to mention to you that sometimes you are going to be asked for this location. And that location requires you to go left on the blue and up on the red. So you have to have, I don't know, the vision in math that tells you direction. So I don't know if I can do this with the big screen. I hope I can. It's going to be dicey, so I'm going to choose not to. I'll scribble and then bring it down. But if I am asking you for that point, oh, I've color-coded, I'm good. That means left and up. And when you have a left measurement, that means, and I'm going to do this in black, that it is a negative measurement, and then the up is a positive measurement. So you've got to know where you're located on the grid when you're asked for this kind of information as opposed to just the values. So this is magnitude, this is length. So we say the length of that line, that red line, is 41.53, or if you're talking really accurately, 43 times sine of 75 degrees. But if you're trying to say a location, you have to indicate that it is to the left on a grid. Okay, we got 2 more questions, just like this. Notation is annoying. And this is the first time we get to talk about bearing. So it depends on what you're driving as to how you talk about bearing. So I'm going to draw a picture again. So it says a ship is 215 kilometers from a lighthouse at a bearing of south 61 degrees west. So here's my picture here. I have to draw myself a little. I don't need my vectors. I just need lines. North, south, east, west. If you need to write them on, like me, to be accurate, then go ahead. Never eat shredded wheat, news, or just you know it. But if I am asking you for a bearing of south 61 west, that means that you have to draw a line south, and then you have to veer off 61 degrees to the west. That's what that's asking you to do. So the 61 degrees is right in here. And the length of this line is 215 kilometers. And we need to know this rectangular component, horizontal displacement, and this rectangular component, vertical displacement. So I'm going to name these something a little bit different. My red is the up and down, so I'm first of all going to make sure I color code things so that I'm consistent. Red is up and down, blue is side to side. Take this and move it over to here so I have some more scribble room and I'm not into the margin. Other thing I'm going to take care of is the fact that this is a 90-degree angle and I do not have my angle in the bow tie, so I'm going to make sure I figure out what 180 minus 61 is. Don't judge. Okay, so it's 119. Oh my gosh, I did it again. $90 minus 61. Don't judge. 29. Okay, so I'm going to call this side displacement vertical vector, and I'm going to call this side displacement horizontal vector. And I'm not going to show as much work as I did the last time because I think I'm better at it the second time around. So I have opposite and hypotenuse. I've got sine 29 degrees is equal to opposite over hypotenuse. I'm not going to put the 1 down. I'm going to say the vertical component of the displacement is 215 times sine 29 degrees. And I'm not even going to write that as a decimal because I don't have to. I do know that that's kilometers. And if you're wondering how displacement shows direction, here's your magnitude. The direction is that I've already said it's vertical. So now I get to do it again in blue. Cos 29 degrees is equal to the horizontal vector component over 215. So the horizontal displacement component is 215 sine 29 degrees in kilometers. Okay, before we do the last question, I am going to have a little hand cramp moment. Okay, before we move on to that next question, I just want to drive home the difference between this and placement on the grid, meaning that direction business again. So these are perfectly good answers for the displacement vertical component magnitude and the magnitude of the horizontal displacement component. That's not a big deal. But if I were to label this on a grid, because this is left, I need my blue measurement with a negative sign. And because this is down, I need my red measurement with a negative sign as well. What did I do? Oh my gosh. Am I ever glad I came back to this? How did that happen? See how the tediousness of this stuff actually makes you make typos? So there, now I'm all good. Wow, I'm glad I came back to that. All right, last question. A newspaper carrier pulls a wagon with a 65 Newton force at an angle of 25 degrees to the horizontal. Oh, big yawn. Determine the horizontal and vertical vector components of the force. So here's the ground. Oh, I thought that was why I was using a ruler. Give me a sec. Here's the ground. And a newspaper carrier is pulling a wagon with a 65 Newton force at an angle of 25 degrees to the horizontal. So I'm being a very bad person and not doing this with a protractor. But I know that in my sketch, rather than scale drawing, this is 25 degrees and this is 65 newtons. And here is my horizontal component and here is my vertical component. And if I check, vertical is red, vertical is red, vertical is red, which makes horizontal blue. And thankfully, my angle is in the right spot. So these are forces, so I'm going to label this. This is the vector force that is vertical. This is the vector force that is horizontal. Now, I have always gone back to trig. And part of that is I know how many formulas you need to memorize in this course, or you need to memorize for this course, or you need to know how to use for this course. So if you prefer not knowing how many there are, you can go back to this if you like. As in, I can take this red thing, I'm going to clone it, and I'm going to shove it over here. And I'm going to take this blue thing, and I'm going to clone it, because I don't have these memorized. I have the trig fully understood, but I don't have these formulas memorized. So I'll do horizontal here, and I'll do vertical here. And I've got my angle in the right position, so blue comes first. The horizontal force vector has a magnitude of 65 times cos 25 degrees. And the vertical component has a magnitude of 25, oh, did it again, 65 for the force, sine, theta is the angle, 25 degrees. And we're done. Technically, I should, if I'm not going to turn these into decimals, indicate that they are newtons. And because this is a right angle triangle, if you take this value and square it and add it to this value squared, you should end up with this value squared because Pythagorean theorem kicks in. So you can leave it as you wish. Okay, so the last thing is this. So this will be on the Google Classroom. This is the stuff from the Red Calculus and Vectors textbook. And I think that might be it till later tonight, or maybe even some this week. But this unit will be done. Woo!